Today we're going to talk about transformations of functions. This is for Math 1508 at UTEP, Chapter 1 of Larson's Pre-Calculus, 10th edition, Section 1.7. Vertical and horizontal shifts. So let's let C be a positive real number. Vertical and horizontal shifts in the graph of y equals f of x are represented as follows. If we add a value C to the y, the graph shifts up c units. If I want to shift downward, I'll subtract c. So we do all the function stuff and then we subtract from the output. So it affects the y values directly. We'll have an up shift or a down shift by adding on the outside of the function or subtracting on the outside of the function. Horizontal shifts, right? Horizontal goes left to right. Those will affect the x values directly. So f of x minus c will go to the right c units. Standard form, x minus c goes to the right c units. A lot like we saw in our circles standard definition, it was an x minus h. So it goes to the right c units. Horizontal shift c units to the left will have an x plus c. In general, the outside is dealing with the y, it's vertical. The inside, dealing with x, is a horizontal. Side note here, let's move this off to the side. If you take what's inside the parentheses and set it equal to 0, you will get the amount of your shift, x equals c, and that is why it goes to the right. Whereas if you take x plus c and set it equal to 0, the x value has now shifted to negative c, and that's why it's to the left. So right and left, based on setting the inside, the part that's messing with x, equal to 0, helps you remember left and right a little bit easier. Reflections. So reflections in the coordinate axes for the graph of y equals f of x are represented as follows. A reflection in the x-axis, meaning the x-axis axis the mirror, a negative on the outside of the function. So a reflection in the x-axis, I might take a standard a square root graph, and if I reflect it, my image will be down here. So reflected in the x-axis uses the x-axis as the mirror, but notice that it affects the y values because the negative's on the outside. It's going to affect the vertical. It's going to be a vertical reflection where the x-axis is the mirror. Similarly, a reflection in the y-axis uses the y-axis as the mirror or the line of reflection, and the negative will be on the inside because a y-axis reflection will change the x values. What was a positive x now becomes a negative x. Again, outside is vertical, inside is horizontal. Shifts and reflections are called rigid transformations because they keep the shape of the graph rigid as they move. It's the same width, it's the same shape. Nothing is moved at all other than left, right, up, down, or maybe flipped over. Non-rigid transformations are shrinking and stretching, and so they distort the graph. Maybe the parabola is thinner, or the cubic graph is narrower. Let's take a look. Vertical distortions. For y equals f of x, the transformation given by g of x equals c times f of x is a vertical stretch if c is greater than 1, and a vertical shrink if c is a proper fraction between 0 and 1. Vertical shrink, think about it as pressing down on the tops of a quadratic so it makes it wider. A vertical stretch, think of it as grabbing the arrows on the endpoints and pulling them either straight up or down or whatever your graph happens to be finishing at, so it makes it narrower. So a vertical stretch is narrower. A vertical shrink, I'm pushing it down, it's going to be wider. Horizontal distortions, the transformation given by g of x equals f of c of x, is a horizontal shrink if c is greater than 1, and a horizontal stretch if c is a proper fraction between 0 and 1. Now what's a horizontal shrink? Think of taking that parabola and pushing it in on the sides. A horizontal shrink is the same as a vertical stretch. It's going to make it narrower. Whereas a horizontal stretch, you're grabbing onto the sides of the parabola and you're pulling it apart. It's going to be wider, like a vertical shrink would be. So a horizontal stretch goes with a vertical shrink. A vertical stretch goes with a horizontal shrink. I remember it as vertical is always on the outside, and it's always normal, right? The plus C on the outside goes up. The minus C on the outside goes down. It makes sense. Whereas horizontal on the inside is opposite of what I would consider common sense. The x minus c on the inside of the function goes to the right. The x plus c on the inside of the function goes to the left. So we have a little bit of opposite going on when it comes to horizontal versus vertical. Now there's a whole series of examples like this. If you get the point after a while, you just want to fast forward, that's cool. But if we take this given graph, just some random graph, the points -4, 2, -2, -2, 0, -2, and 6, 2. And we're going to transform them using some of our transformations that we just talked about. So first of all, y equals f of negative x. The negative on the inside is a horizontal reflection. Because it's on the inside, it affects the horizontal. The y-axis is my mirror. So 6, 2 becomes -6, 2. 0, -2 is on the y-axis. It stays where it is. -2, -2 is flipped over. So it becomes +2, -2. And finally, the point +4, 2. We flip the sign of just the x values. For y equals f of x plus 4, and this graph is going to stay the same in all of these examples. Y equals f of x plus 4, this is a vertical shift up 4 units. So all I'm going to do is add 4 to each of the y values, and I have my new points that I could plot. Notice this, assuming I could graph things that look similar using this pen system, they're the same graph, it's just shifted up. Otherwise, same width, using your imagination. Number 3, y equals 2 times f of x. The 2 is on the outside, so I'm going to stretch this graph vertically because it's on the outside. Once I do my operation to it, my function, then I'm going to multiply my y values by 2. And so that's all I do. Instead of the point -4, 2, I now have the point -4, 4. All the y values, all the x values stay the same. All the y values get doubled. Double the y values. Now let's do some combinations. The negative on the outside is a vertical reflection, and the x minus 4 on the inside tells us to go right 4 units. Right, on the inside, it's right or left. On the outside, it's vertical. So I'm going to go right 4 units and flip over my y values. So I add 4 to all of my x values. I change the sign of all of my y values, and I have my new graph. F of x minus 3 is down 3. I keep the same x values. I subtract 3 from my y values, from the given points. Subtract 3 to get the new coordinates. Negative f of x minus 1 is a vertical reflection, and then down 1. So I take care of this multiplication, right? Order of operations, multiplication comes first, and then down 1. So I flip it over. Same x values, x hasn't been messed with at all. So the same x values, I multiply the y by a -1, and then I subtract 1. So that's a -2 minus 1 gives me -3. Flip it over, makes a +2. When I subtract 1, I get a +1, and so on. Now, on the inside, a horizontal shrink by a factor of 2, right? Because we're multiplying by 2 on the inside. It's opposite of common sense, so it's a shrink. Horizontal shrink. I set little equations up. Let's see if I could do this without messing up my picture. I set 2x equal to -4 and get x equals -2. And that's my first x value. I could do these little equations for each one. 2x equals -2. Well, then x must have been -1. If 2x equals 0, x equals 0. And if 2x equals 6, then x must have been 3. Notice how it shrinks it. It's narrower graph than what we had to start with. So a horizontal shrink by a factor of 2. All right, let's do some different types of examples. The given function, g of x equals x minus 8 all squared is related to one of the parent functions that we described in section 1.6, also known as the lecture on the library of parent functions. So we want to identify this parent function, that'll be in blue. We're going to describe the sequence of transformations from f to g, that'll be in green. We're going to sketch the graph of g, and it's going to be a sketch, so I'm not going to be very particular with my scaling and that sort of thing, in gray. And then we're going to use function notation to write g in terms of f. So we got a lot going on here. Let's take it a step at a time. If g of x is, in parentheses, x minus 8, all squared, my parent function is squared. Right? That's the overwhelming function thing that's going on. But what are we doing to the squared? We're subtracting 8 from the x inside the operation of squared. Subtracting 8 from x directly affects x, so it's a right-left idea. Because it's x minus 8, we go right 8 units. That's it. That's the only thing that we've done to the function. So the graph would just be a parabola with a vertex at 8, x-intercept of 8. In general, if f of x equals x squared, we would write this function, g of x equals x minus 8 all squared, as g of x equals f of x minus 8. So the squared is the parent function, and so that's where the f comes in. F of what? F of x minus 8. Example 2, g of x equals negative, parentheses, x plus 10 all squared, with a plus 5. Again, this is a basic squared function, and then we've messed with it. How did we mess with it? We reflected vertically because it's on the outside. A vertical reflection goes across the x-axis as your mirror, right? Goes up, down. I've gone left 10 units. I've gone up 5 units, left 10 units, up 5 units, and reflected. It would look like this. If I wanted to write this in function notation, remember f of x is x squared. And that's the only thing we really replace. We still have the minus sign for a reflection. We still have the x plus 10 to tell us that we moved to the left 10. And we still have our plus 5 on the outside to tell us we went up 5. But instead of calling it the squared, we call it f of x plus 10 with a negative in front and a plus 5. Number 3, g of x equals x plus 3 cubed minus 10. The cubed tells us our parent function is f of x equals x cubed. The x plus 3 in parentheses tells us we went left 3. The minus 10 on the outside tells us we go down 10. So I take the standard graph of x cubed, which is this lazy looking graph, and I move my 0, 0, my origin point, to the left 3, down 10, and I did my best to make a little cube graph here. In general, if f of x is x cubed, we could rewrite this as f of x plus 3 minus 10. One more. G of x equals 6 minus the absolute value of x plus 5. What's the function going on? What's the operation? It's the absolute value. So f of x, our parent function, is the absolute value of x. The 6 tells us to go up 6. The minus sign on the outside is a reflection, a vertical reflection that goes across the x-axis. And we go left 5, right? Adding 5 to the x directly tells us to go left 5. Left 5, up 6, reflected. Instead of writing as absolute value, I could use the idea of the parent function, f of x, and rewrite this as 6 minus f of x plus 5. Last example of this type. G of x equals a negative 1/2 square root of x minus 3 and then plus 1. So we have a lot going on here. Basically, it's the square root function that we've really jacked with. Let's take a look. F of x equals the square root of x. The negative in front is a vertical reflection across the x-axis. The 1/2, right, is a proper fraction between 0 and 1, so it's a vertical shrink of 1/2. Under the radical inside the function itself, I subtract 3, therefore I go right 3. On the outside of the function, I add 1, so it's up 1. So a normal radical function has the basic idea of the top half of a parabola laying on its side. I will flip it over. Let's see if I can flip that over here. I'll flip it over. And then I'll make it a little bit narrower. And then I will shift it to the right 3 and up 1, landing here. My graph starts at 3, 1, and it's going to be the bottom half of a parabola now because of the reflection. It's a little bit narrower than the standard square root function. Also, in function notation, we just replace the square root with the f of x. Don't overthink this step when it comes to the homework. Alright, so given a function, we could describe the transformations, but if we're given the transformations, can you write the function? Let's take a look. Write an equation for the function described by the given characteristics. The shape of the quadratic function. So I know f of x equals, and I'll have parentheses, x something squared. Alright, so in blue, I write that part down first. But shifted 3 units to the right, so I'm going to subtract 3 on the inside. And 7 units downward, so I'm going to subtract 7 on the outside, and there I have my function. The shape of the cube function, so f of x equals, and then I'm going to have some parentheses with x and cubed. Shifted 6 units to the left, 6 units to the left. 5 units downward, so I'm going to subtract on the outside after I finish the cube. And reflected in the y-axis. If it's reflected in the y-axis, it has to be inside the function, right? Reflected in the y-axis is a horizontal, so it has to be inside the cube, and that's why I have this double set of parentheses. This negative can sometimes get a little confusing when we set up our functions with transformations. 2 more. The shape of the absolute value function, so f of x equals absolute value x. All right, and I leave some blanks. 4 units to the left, so I'll add 4 on the inside right next to x. 8 units upward, so I'll add 8 outside of the function after the operation is finished. And that's the end, and I leave it there. Number 4, the shape of the radical function. So f of x equals the square root, and then I have an x in there. Shifted 9 units upward. All right, 9 units upward. I'm going to add 9 on the outside of the radical. After the radical is finished, then I add 9 to the y values. Now it's reflected in both the x-axis. X-axis reflection is vertical, so the negative's on the outside. And the y-axis reflection affects the x values, right? It affects the horizontal, so there's a negative on the inside as well. So our domain now is x values have to be negative numbers. That way we have negative, negative. We have a positive underneath the radical, and we can deal with it. Double reflection. That's a good one. This concludes the lecture for transformations of functions. Thank you for listening.